A capacitor is a device that stores electrical energy in an electric field. Here, some different types of capacitors are displayed. Even though each one looks like different, if you look inside these capacitors, they have two pieces of conducting plates separated by a dielectric. Dielectric material is an insulating material which opposes the flow of current. The plates are made up of metals like aluminum, and the dielectric can be made up of any kind of insulating material such as paper, glass, ceramic, or anything that blocks the flow of current. Now let us learn how a capacitor works. Initially, the two conductors are electrically neutral. That means they have equal number of positive and negative charges. When we apply voltage between these two plates, electrons from the top plates are attracted towards the positive terminal of the battery, and these electrons are pushed towards the bottom plate of the capacitor through the negative terminal of the battery. However, because of the dielectric in between the conductors, the electrons which are collected at the bottom plate of the capacitor are not able to cross the barrier. So, electrons start to accumulate on the bottom plate. After some time, the top plate has shortage of electron while the bottom plate has excess of electron. So we can say that top plate become positively charged and bottom plate become negatively charged. Because of the charged particles, a potential difference is developed across the plates. Transfer of electron will continue till this potential difference is equal to the potential difference across the battery. Because of this potential difference, an electric field will develop between the plates. This electric field is given by E equal to V by D. This electric field is directly proportional to the potential difference and inversely proportional to the distance between the two plates. If you increase the potential difference of the battery, electric field increases. If you increase the distance between the plates, the electric field decreases. Even if you remove the voltage source, the capacitor stores energy in terms of electric field. This process is called charging of capacitor. Let us learn how dielectric affect the charging of a capacitor. Dielectric change their orientation based on the charges on the two plates. So, the molecules aligned themselves with the electric field in such a way that the negative pole of the dielectric faces top plate and positive pole of the dielectric faces bottom plate. This will enable more electrons to be attracted to the negative plate by repelling more electron out of the positive plate. Once the capacitor is fully charged, if you remove the battery, it will hold the electric charge for a long time. If a load is connected and turn on the switch, electrons from the top plates started to move towards the bottom plate. Flow of charges produce current and the bulb glows. This process continues till both plates become neutral. This process is called discharge of capacitor. After some time, there is no excess of charges in the bottom plate. After discharge, both plates are in neutral and the bulb stops glows. So, capacitor is a device which stores charge, but not all capacitors will store same amount of charge. If one capacitor is connected with a battery, it might store small amount of charge. If another capacitor is connected with the same battery, it might store large amount of charge. The ability to store charges in a plate is called capacitance. The capacitance of the capacitor is the number that tells you how good the capacitor is at storing charge. A capacitor with a large capacitance will store a lot of charge. A capacitor with a small capacitance will only store a little charge. So, capacitance equals the charge stored on the capacitor divided by voltage across the capacitor. So, we can say that C equal to Q by V. Q in this formula is referring to the magnitude of charge on one side of the capacitor, and V in the formula is referring to the difference in potential between the two metal plates. If 9 microcoulomb charges are stored in a fully charged up capacitor which is connected to a 3-volt battery, then the capacitance of the capacitor is 9 by 3 equal to 3 microfarad. Practical capacitors are designed in a variety of shapes, some of which are shown here. We have C equal to Q by V. We know that V equal to electric field into distance. Substitute V in C, we will get C equal to Q by ED. We already know that the electric field between the two plates is given by E equal to sigma by epsilon 0 and Q equal to sigma A. Substitute E and Q in C, we will get C equal to epsilon 0 A by D. The unit of capacitance is farad and the practical unit is microfarad. So we can change the capacitance of the capacitor by altering the physical characteristics of the capacitor. By increasing the area of the plate, the capacitance of the capacitor increases. By decreasing the distance between the two plates, the capacitance of the capacitor increases. Similarly, by changing the dielectric material between the two plates, the value of the epsilon 0 changes. A vacuum is a poor dielectric and is given a relative permittivity of 1. Other dielectrics are measured relative to a vacuum. Air is roughly the same. Paper is about 3 times better than air. Alcohol and water, which have polar molecules, make particularly good dielectrics. Mica is at least 5 times more effective than air. So, by adjusting area of the plate, distance between the plates, and by choosing proper dielectric, we can design our required capacitor.